All right, welcome again. We want now to see how can we determine the thickness and the dipping amount for the dipping interface when seismic waves travels from the surface towards the dipping interface and get reflected to the geophone. How can you determine the dipping amount? Well, from the equation that describes the travel time of the waves for the dipping interface, Tx squared, let's say the travel time at a distance x from the source to the geophone, and that's why it is T squared is equal to x over v squared plus 2h over v squared minus 4x h, the sine of beta over v squared. But we were using j, not h. Therefore, the exact expression is t squared is equal to x over v squared plus 2j over v squared minus 4x j sine of beta over v squared. If you remember, this is the equation that describes the total travel time of the waves that are reflected on the dipping interface. How can we extract important parameters like dipping and the thickness of the layer? How? Well, we know that if we draw the graph for the dipping layer, for the signals that comes from the dipping layer, if we draw the graph, then it will have the minimum amount. It will show the value of the travel time at x is equal to 0. And from those conditions, we can put the supportive environment to get the value of the dipping amount and the thickness of the layer. How do we do? Where we differentiate the time with respect to x. Therefore, we get 2t dt dx is equal to 2x over v squared, this is 0 of course, minus 4j sine of beta over v squared. So at x minimum, at minimum value of x, then dt dx is equal to 0. Then the question becomes 0 is equal to 2x over v squared minus 4j sine of beta over v squared, which is of course equals to saying x is equal to 2j sine of beta. But now x is a minimum, of course we should use minimum term, and therefore x minimum is equal to 2j sine of angle beta. This can be the equation number 1. This is the equation number 1. But at x minimum, what will be the t minimum? At the expression for the t as the function as the function of x is this one here. But when x is minimum, now t minimum squared will be equals to substitute substitute x minimum into the position of x, then it will be is equal to 2j sine of beta over v, then squared plus 2j over v squared minus 4 xj sine of beta over v squared. But sorry, instead of x we should substitute the value of x minimum, which is the value of x minimum, which is 2j sine of beta. Of course it is not x. Therefore, the equation will be given as T minimum squared is equal to 4, if we open the brackets, 4j squared sine squared beta over v squared plus 2j over v squared. Here, if you open the brackets, you have minus 8j squared sine squared of beta over v squared. This term here and this term here will reduce each other, and then we shall have 2j over v squared minus 4j squared sine squared of beta over v squared. Now it seems that you can factorize 2j over v squared out. Then we shall have 1 minus sine squared beta. But 1 minus sine squared beta is equal to cosine beta, and therefore t squared minimum will be equals to 2j over v, then squared, this is the cosine of beta, the cosine squared of beta. Therefore t minimum, if we apply the square root each side, will be the same as 2j over v, then the cosine of beta. This is the value of t minimum. Let's call this is the equation number 2. This is the expression for the t minimum, and this is the expression for x minimum. What is the value of t when x is equal to 0? I mean t naught. When x is equal to 0, let's return back to the expression for the tx. When x is equal to 0, substitute x here, we shall have only one term, and therefore the value of t at x is equal to 0 will be equals to 2j over v. Let's call this is the equation number 3. All right, if we take the we divide the equation number 2 to equation number 3, then you will find that t minimum over t naught is equal to cosine beta. Therefore, t minimum over t naught is equal to the cosine of angle beta, and therefore beta angle, or the dipping angle, will be given as the cosine inverse of t minimum over t naught. Okay, and then what other important parameter we can extract there? How can you get the thickness? Remember from our triangle, if you remember from our triangle, this one here, from this geometry, you find that this is right angled triangle with the hypotenuse equals to j and the adjacent is equal to h. Therefore, you'll find that the cosine of angle beta is also equals to h over j. H is the thickness, and therefore h, or the thickness, is given as the j, value of j, you multiply by the cosine of angle beta. This is the expression for the thickness, and this is the expression for the dipping amount. What other important parameters we can extract from these expressions? Of course, what other important parameters we can extract from these? We find that t naught is equal to 2j over v. T naught is equal to 2j over v, and therefore v will be equals to 2j over t naught. So we can extract the velocity, the thickness, and the dipping amount. Remember that the t minimum, t naught, and will be read directly from the graph. If you draw the graph, it will show the minimum value, the value of the t at x is equal to 0. So the expression for the dipping amount is this one, Then the expression for the thickness is given by this expression, and the expression for the velocity is given by this. Thanks for watching.